Imagine that a small black hole flies through your brain as we speak, leaving behind a hole. I read this in a new physics paper the other day. Maybe that left a hole in my brain, but the more I thought about this idea, the less crazy it's become. You might think that by now physicists have figured out when and how black holes form, but actually they know less today than they knew a decade ago. Physicists used to think there are two types of black holes, those which form when big stars run out of nuclear fuel and collapse. These are the stellar mass black holes and should have masses a few times that of our Sun. And then there are supermassive black holes which were seeded by the collapse of stars very early in the universe. They grow by swallowing other stars and gas and joining with other black holes. Some of them grow as big as 1 billion times the mass of our Sun. That was the theory, but then data got in the way. Gravitational waves detected from black hole mergers seem to show that the stellar mass black holes are much heavier than they should be, sometimes by up to a factor of 10. And computer simulations have shown that supermassive black holes simply haven't had time to grow to the sizes that we observe. Observations from the James Webb Space Telescope also say that there seem to be more of these big black holes in the early universe than we thought. So maybe we don't properly understand how black holes form to begin with. There are only two situations that we know when the conditions to make a black hole occur naturally. The first is the collapse of a star. The other is fluctuations in the superhot and dense plasma which filled the early universe. Imagine a soup so clumpy it collapses to black holes. That's the idea. And these black holes could be of pretty much any size. They're called primordial black holes, and they would have been around before the first stars. Primordial black holes are one of the candidates for dark matter. It sounds like an appealing idea at first because one wouldn't need any extra stuff, but the idea never worked out very well. By the way, this video comes with a quiz that lets you check how much you understood. The issue is that we don't just need a little bit of dark matter here and there. The stuff makes up 80% of matter in the universe. That'd require a lot of black holes. And if there were that many black holes, they should have other observable consequences besides their gravitational pull. Depending on their initial mass, they would have evaporated already, leaving behind flashes of light, or they'd make gravitational lenses, or they would sometimes pass through stars and make them collapse. We haven't seen any of that. This is why the idea that primordial black holes make up dark matter was never very popular. But that doesn't rule out primordial black holes. It just says that they aren't a good explanation for dark matter. But forget about dark matter. Shouldn't we look for primordial black holes on their own right? I don't know about you, but I'd like to know if there are literally black holes going through my brain. Well, this is where the new paper comes in. The authors do some calculations for what the consequences would be if small black holes passed through asteroids or planets or people on these planets. If the black holes are large enough, they might leave a planet or asteroid hollow in the core. This could happen because the black hole might get trapped and then get stuck in the inside and eat up stuff that falls in. If they are much smaller than the object they pass through, they'll leave tunnels. These tunnels can be ridiculously tiny. Just to give you a sense of scale, a black hole with a mass of 10 microgram would have a diameter of just about 10 to the minus 35 meters. They're so tiny they basically wouldn't do anything. They're not heavy enough to attract atoms and also wouldn't slow down and get trapped if they passed through us. Just a little bit of stellar acupuncture. As they write in the paper, such a black hole should not be fatal when passing through the human body. However, the bigger the black holes are, the easier they become to detect. The authors of the paper say we should look for holes that suddenly appear in materials. If the black holes are bigger, they might give rise to earthquakes whose epicenters seem to move. These might be hard to detect on Earth, but it might work on the Moon. One thing that they seem seem to be missing in the paper, though, is that, well, we do have a lot of very sensitive particle detectors, and the guys at CERN would probably have noticed if a hole appeared in one of them. Similar searches have also been done with old stones that have been examined for tracks, and they didn't find anything. Unless a black hole ate the paper, so who knows? That said, the idea that black holes pass through our brains and eat up a few neurons every once in a while could really explain a lot. A lot of computer scientists believe that if we just make AI models big enough, they'll eventually learn pretty much everything, including reason. And I certainly hope they will. I mean, wouldn't you want an autonomous vehicle to follow basic laws of logic? Officer, if I didn't hit anyone, I wouldn't be here. But I'm here, so clearly I didn't hit anyone. But I like my dystopias to have scientific support. So when I heard that a group of researchers has demonstrated that the current AIs can't reason, I of course had a look. What is reason? I'll leave this to your favorite 3-hour philosophy podcaster to discuss. For the purposes of this video, reasoning will just mean getting basic maths and logic right. You know, arguments of the sort, if pizza, then no pineapple. I hope that's clear. The AIs that we use today were not born knowing logic. They're almost all of the same type. Deep neural nets trained on large amounts of data, sometimes with reinforcement learning. These AIs learn to recognize patterns and to interpolate and extrapolate from them. No one knows how much they can learn if you feed them more and more data. Some computer scientists believe that as the models are trained on more and more data, they acquire emergent abilities. Indeed, they say this has already happened. These emergent abilities are unexpected new features that have suddenly appeared as models got bigger, such as, for example, the ability to unscramble words or to understand relative locations in space, including geographic maps. They've also acquired mathematical abilities. If you look at how these models perform on some benchmark tests, then their performance on standard maths tests has dramatically improved as the models have gotten bigger. This naturally raises the question, will they just go on to learn everything? I strongly doubt that these emergent abilities will ever give rise to sound reasoning skills. The models can learn patterns that are in their training data, but language is not good for encoding logic or maths in the first place. It's just too vague, and people make logical mistakes all the time. Like, I've heard that some of them put pineapple on pizza. But the question of whether deep neural nets can reason is more relevant today than ever, because many companies might use them for cases that require solid reasoning abilities. It's not just autonomous vehicles. Imagine an AI advising governments, or the military, or, heaven forbid, pizzerias. I don't know about you, but I want to know whether AIs can reason. And the easiest way to test this is with maths questions. So far, I've not been impressed by the maths abilities of today's large language models. Here is me asking GPT for the smallest integer whose square is larger than 5 but smaller than 17. It gave me 2 garbled answers, according to which the answer is 3. The correct answer is -4. You can see what goes wrong there. GPT neither knows what integers are nor what order relations are. It just throws together text and maths symbols that look more or less plausible. The output it provides is close to the correct answer in the sense that the text is semantically similar, but it's very far in terms of mathematical accuracy. In the new paper now, a group of researchers from DeepMind and Apple systematically studied this very question. They looked at the reasoning capabilities of large language models, including the newest GPT and Llama, with a common maths test called GSM 8K. That's grade school maths with about 8K questions. It's not a complicated test. It consists of questions like, James writes writes a 3-page letter to 2 different friends twice a week. How much pineapple does he put on pizza? Just checking if you're listening. The question is, how many pages does he write each year? And in case the police come to ask, the correct answer is 624. For the new study, they altered the maths questions by changing names or numbers or adding unnecessary text. They found that the maths performance significantly dropped for all models. This strongly suggests that the models don't actually reason. They just draw on language relations and output something similar to what they've learned. Though the drop is just a few percentage points, so it's not as bad as it sounds. Then again, this was a super simple maths test, so it may be worse than it sounds. One can also argue that it'd have been only fair to compare the results with that of humans instead of asking for a perfect score. If you ask me how many pages James writes per year, I might well answer pineapple just to get rid of you. Indeed, just a few days after this study came out, a parody paper appeared with a comprehensive analysis of human reasoning from the Chicken Little Center for Stopping the Sky from Falling. The fictional authors, who include Cognos Biasum, claim, among other things, that the fact that some humans still advocate communism, even after having been presented with the undeniable evidence that communism has never worked anywhere in the entire history of the world, is proof that Homo sapiens are basically crazy monkeys who excel at creative storytelling rather than genuine logical analysis. I believe they're joking. But why humans learned logical reasoning to begin with is a good question. I'd guess we learned it more or less because nature obeys the rules of logic. This makes me think that the more AIs learn about physical reality, the more likely they are to understand reasoning. Basically, I'm saying teach them physics. What else would you expect a physicist to say? Climate scientists on social media have become somewhat of a pain. Many of them raise the impression, deliberately or accidentally, that the science demands action. They seamlessly go from "this is what we know" to "therefore we need to do this," which is totally outrageous. It's also what I've been doing, so I guess it's okay. So is it or is it not okay to mix science with activism? I am of 2 minds about this. I was thus very interested to see the issue discussed in 2 comments that appeared in a Nature journal called Climate Activism. In the first comment, a climate scientist by the name of Ulf Bündgen complained that some climate scientists hold quasi-religious beliefs that undermine academic principles and diminish academic credibility. His comment was cheered upon by climate change deniers. Then 3 climate scientists who clearly felt attacked replied that it's not possible for science to be value-free, therefore we shouldn't try. This supports my theory that insanity loves company, especially in academia. But let's have a look. Bündgen starts, "I'm concerned by climate scientists becoming climate activists because scholars should not have a priori interests in the outcomes of their studies. But scientists almost always have an outcome that they hope for, unless possibly they're bots, and maybe that'd be better for everyone involved. But until we get there, the important thing is that when the results come in, you take them for what they are." Bündgen goes on, "Characteristic for the yet unfolding phenomenon is an intermingling of science and policy in which political decisions are believed to be without any alternative, and without self-critique and a diversity of viewpoints, scientists will ultimately harm the credibility of their research and possibly cause a wider public political and economic backlash." He also gives examples for how he thinks this credibility has been harmed. One is that the Intergovernmental Panel on Climate Change, in its latest summary for policymakers, tends to overstate scientific understanding, a problem that I've also talked about. Another example he names is the ongoing pseudoscientific chase for record-breaking heat waves and associated hydroclimatic extremes, which I've also talked about before, so I guess I agree with him more than not. He fears for the reputation of his discipline, for good reasons. In the reply, the authors argue that we should redefine the boundaries of acceptable influence of values in scientific communication. They say that reaching a state of neutral science is not only impossible but undesirable, and clarify that neutrality here refers to science free from values, which should not be confused with objectivity, which has been defined as science free from personal biases. That sounds good, but while it's technically true that biases and values are two different shoes, scientists who push their values on other people become suspect of being biased. And to harm the reputation of a discipline, this suspicion of bias doesn't have to be correct. It just needs to exist. They go on to claim that recent research generally finds that climate policy, advocacy, and civil disobedience does not diminish the credibility or trustworthiness of these scientists. Really? Policy advocacy does not diminish a scientist's credibility, regardless of the policy? If I go and advocate homeopathy against climate change, wouldn't you think that this might damage my credibility? Should we look at the references? What do you think? Look at the references? Okay, I heard you clear and loud. The first reference is for a study which measured the perceived credibility of an invented scientist. They found that the credibility was high in 5 of the 6 message conditions, but suffered when the scientists advocated for a specific policy, building more nuclear power plants. So the credibility was fine until the scientists advocated a policy that the study participants didn't like. The conclusion of the paper says, our results suggest that scientists who wish to engage in certain forms of advocacy might be able to do so without directly harming their credibility. This study says the exact opposite of what the authors of the comment think it says, namely that advocating policies can harm a scientist's credibility. The second reference is titled Majority of German citizens, US citizens, and climate scientists support policy advocacy by climate researchers, but it doesn't say anything about the scientists' credibility. And the third reference is about a study in which a fictional scientist supposedly participated in civil disobedience. They find that this did not undermine the credibility of their research findings. But we're not talking about the credibility of research findings. We're talking about the credibility of the researcher. So the authors of the replying comment dismiss the concerns raised in the first comment based on references that say the opposite of what they claim it does, which ironically is exactly the quasi-religious pseudoscience problem that the first comment complained about. Tells you all you need to know about academic discourse. I don't trust these mini-studies in sociology, but they seem to say the public uses scientists to support whatever values they have already. And beware confirmation bias, that agrees with my experience. That said, every scientist has values, and in my opinion, it's totally okay for them to advocate policies. However, I think they need to make clear where the science ends and their opinion starts. You can calculate the risks of climate change, but you can't calculate what we should do about it. This scientist is also of the opinion that environmental protection doesn't need to be difficult. You can make a big difference with little effort just by supporting my friends at Planet Wild. Every once in a while, I read a paper that makes me slap my forehead and say, I wish I'd thought of this. This is one of those. Mathematicians have for the first time described a new pattern in nature. I don't want to say that they discovered it because it's been there all along, probably sipping tea and quietly judging us for taking so long to notice. Remember the Einstein one-stone shape that made headlines earlier this year? It's the first single shape that can fill a plane without leaving gaps. You can now buy those as puzzle stones, and I have little doubt that nerds all over the world are tiling their bathrooms with it. Mathematicians have a fascination with patterns like this that fill spaces without without leaving gaps. And who can judge them? Gaps are so 2005. And we also see space-filling patterns a lot in nature. If you want to fill a plane, it doesn't work with circles, but it works with hexagons. It doesn't work with pentagons, but it works with triangles. And there are more difficult tilings that don't repeat, which we find, for example, in quasi-crystals. This new finding is also a tiling, but one that doesn't use polygons as tiles. It instead uses tiles with soft corners. In these soft corners, the edges from two sides approach each other on a curve, and then they end up parallel to each other. That makes one sharp peak, but then the adjacent tile has a soft edge. The interesting thing about this is that you can't do this in every corner of a polygon. Then it'd no longer fill the plane. So the mathematical question is, how do you distribute the soft edges? It depends on the type of polygon. Here you see some examples for hexagonal lattices with soft edges and the various ways they can be tiled. And these are various ways to soften a rectangular lattice. These types of shapes indeed appear in nature, which is what makes this so interesting. For example, if you cut an onion, you get these soft-edged shapes as part of the onion. Or if you look at wheat grains, they have similar shapes. Or returning to the onion, if you look at the individual cells under the microscope, you'll see that they use these kinds of softened corners, though the pattern doesn't repeat regularly. In 3 dimensions, there are even more shapes. Interestingly, the authors found that if you use soft edges, then in 3 dimensions, a shape might no longer have any corners. That sounds super unintuitive, but it'll make sense, I hope. If you look at the illustration from the paper, you see that in 3 dimensions, the shape has edges, but the corners are all rounded off. The cool thing about this is that if such shapes appear in nature, there's almost certainly structural reasons for this. Using rounded corners might reduce pressure and improve stability or flexibility. And once we know that, these shapes might come in handy for man-made designs. The mathematics mediates between observations and applications. It's also a lovely illustration for how we have only just begun to learn how much and which mathematics nature uses. Remember Eugene Wigner's famous essay about the unreasonable effectiveness of mathematics in the natural sciences? I think that the unreasonable thing is not that mathematics is effective in the natural sciences. It's that it's not effective in the other sciences. And why is that? It's because we haven't yet found the right mathematics. This is especially true when it comes to emergent properties of increasingly complex systems like humans or human societies. The patterns that we see in plants and animals, I believe, are an important intermediary step on the way to understanding this complexity. They are also just beautiful to look at and have undoubtedly inspired many young scientists to pursue a career in research. I know you know me for calling out the bias that appealing to beauty can bring, but it's also a great motivator. The problems with beauty and science arise once we start using it as a guide rather than a motivation. The more we've learned about the natural world, the better we've understood that all the complexity around us goes back to remarkably simple mathematical laws. It suggests an underlying unity, a structure that governs everything from the growth of a flower to the formation of galaxies. Or does it? Maybe the search for such universal principles is just our human desire to uncover order and harmony in a meaningless space-time splattered with particles. Whatever is really going on, mathematics has indeed been remarkably effective for understanding nature and also for allowing us to shape it to our needs. And I have a feeling that the question of just why that is so will still be discussed in 1,000 years, hopefully in an interstellar metaverse in a virtual room that has only soft edges. Thanks for watching. See you tomorrow.